Okay. So good afternoon. We are going to start the MAHEPA workshop on safety and HMI considerations in hybrid electric aviation in a few minutes. Waiting for everybody to connect online. We have an attendance mostly online through the streaming. So just be patient for a couple of minutes, please.
With the constant growth of air traffic, the pressure on the environment is rising, and so the use of alternative fuels and powertrains is becoming a necessity. To ease the negative impact of aviation on the environment and to provide cleaner technologies, Project MAHEPA was launched with the support of the EU Horizon 2020 programme. A team of various experts gathered with one sole purpose: to tackle the challenge of more sustainable aviation. Within the MAHEPA project, 2 new hybrid electric aircraft were developed. The first one uses a fuel-driven generator coupled with lithium-ion batteries to power the electric motor, while the second relies on hydrogen-fed fuel cells to produce power enabling zero-emission flight. The MAHEPA Panthera is a 4-seat hybrid electric aircraft, a quieter and cleaner version of the groundbreaking Pipistrel Panthera that has captured the minds of the aviation community worldwide since 2013. The aircraft provides quieter takeoff and flies with less emissions than a conventional aircraft due to its much more efficient powertrain. Panthera can reach a maximum speed of approximately 170 knots and can fly over a range of approximately 1,000 kilometers. It took years of work and experience to realize the idea of this aircraft.
The MAHEPA Panthera hybrid electric aircraft is giving us a clear example of how it is possible to fly greener. This aircraft has much lower fuel consumption, emissions, and last but not least, it is much quieter. Thanks to MAHEPA project, we are showing that change in aviation is possible, and we are doing it now.
The second aircraft is HY4, a visionary emission-free hydrogen-driven aircraft. The HY4 is the first 4-seat electric aircraft with the most powerful hydrogen-based fuel cell system ever used to fly. It enables completely emission-free flights over short or long distances. The HY4 can reach a maximum speed of approximately 200 kilometers per hour and, depending on the flight profile, can fly over a range of up to 750 kilometers.
Our MAHEPA project gives us the opportunity to develop emission-free electric flight with hydrogen, and together with our partners we can show that emission-free aviation is possible.
The MAHEPA project succeeded in flying 2 innovative aircraft and set a clear roadmap for the sustainable future of aviation.
So, welcome everybody to the MAHEPA Workshop on safety and human-machine interface considerations in hybrid electric aviation. This is a workshop connected to the final event of the MAHEPA project. MAHEPA stands for Modular Approach to Hybrid Electric Propulsion Architecture, and as you have seen from the video, this project, sponsored by the European Commission under the Horizon 2020 research program, has reached amazing results in delivering hybrid electric propulsion technologies for aviation. We are going now to present a workshop dedicated to 2 of the main aspects related to the implementation of hybrid electric aviation in the near future, thanks to the great results obtained through this project. I'd like to introduce myself. I'm Lorenzo Trainelli. I am a professor at Politecnico di Milano. I had the privilege to coordinate the Politecnico di Milano unit in the MAHEPA project, which is a large and ambitious project run by a consortium of 8 partners involving companies, Pipistrel, Compact Dynamics, and H2Fly, research centers, DLR, and universities, the University of Maribor, the University of Ulm, Technical University Delft, and Politecnico di Milano. A large effort that delivered high TRL realizations, which are representing building blocks for the future of hybrid electric aviation in view of a much lower environmental impact of aviation in the future. Our workshop today, coming at the end of the project, will tackle 2 important aspects related to hybrid electric aviation. The first one is safety. We will have 3 panelists talking about safety in a moment. Standard practices for hybrid electric technology is the first topic, delivered by Fabrizio Gaspari from Pipistrel Vertical Solutions. Then innovative and safe hybrid electric architectures. The speaker will be Dr. Fabrizio Oliviero from Technical University Delft. And we'll finish with the topic integrating new concepts in safety, reliability, and efficiency, delivered by Dr. Sumantra Bhattacharya from Ulm University in Germany. After that, we will have a panel discussion and a short break before taking again the stage with the second topic, which is HMI, human-machine interface, novel cockpit environment. I will introduce the panelists just after the pause. I would like to ask our guests, both in the conference room and connected online, to pose questions to our panelists in the panel discussion. Online connected guests may post their questions on the comments in the YouTube channel, so we will gather your questions and include them in the discussion. Okay, so that said, I think we may start with the first panelist, Fabrizio Gaspari, who's been the leader of the MAHEPA project as project coordinator from Pipistrel Vertical Solutions. Fabrizio has been leading the MAHEPA project in the past few years, leading the consortium to the great achievements you have seen in the video. He will talk about standard practices for hybrid electric technology. Please, Fabrizio.
Yes, thanks, Lorenzo, for the good introduction about the workshop. So yeah, besides being the coordinator, I'm actually a safety engineer in Pipistrel, so I deal with safety more or less every day. So I will briefly introduce you about the topic and what are the changes that, in safety when it comes to hybrid electric technology. So already the title of this presentation is quite strange, because when it comes to hybrid electric, there's nothing standard, basically. So probably the title was not the best choice, but anyway, I will try to to go over it. So first, what is safety? I mean, we have to understand, to have a common understanding of what we mean with safety. So safety, okay, is the state of being safe and also, being protected from harm or other non-desirable outcomes. But this definition basically is not saying anything very helpful for the aviation sector, because safety is mostly the control of some recognized hazards, and in order to achieve what I said, what I wrote, an acceptable level of risk. So risk will always be there, and safety analysis are basically ways to control it and to make it low enough so that the risk is at an acceptable level. So which are the ways actually to understand if the level of risk is acceptable? So there is a standard approach that has been used in the past decades, and it works perfectly, and it's well recognized all around the world, and by authorities, agencies, everybody. And it's pretty straightforward, so I will briefly introduce it to you. So at the beginning, depending if it's aircraft or system level, of course the first thing to do is to identify the system functions or the aircraft functions and the failure conditions related. So this is done through the so-called FHA, which is Functional Hazard Assessment, basically where you derive the very high-level safety requirements. So you understand which are the failure conditions of a specific system or at aircraft level, and then you derive the safety requirements. Then how to meet these safety requirements is another story, and it goes as follows. So after the FHA is done, the preliminary aircraft or system safety assessment is done. So in the design process, there is a proposed architecture that will hopefully meet the safety requirements. And so in this PSSA process, we analyze if the proposed architecture could actually meet the safety requirements, and you budget a certain probability of failure to a specific system. So after having done this, you actually can proceed with the hardware or software design. So all this is on the from top to bottom, but at the end you have to verify that these requirements are actually met. So this verification is done in the system or aircraft safety assessment process, where you validate and you verify that your requirements are actually met by the actual architecture. This is not all, because there's always a common cause analysis. So you have to understand if the independency that you claimed in the architecture is really there, or if there's any particular risk that could make your assumptions wrong and all these things. So this is the standard approach. It has been used for many decades, as I said, And in principle, it works also for novel propulsion technologies or novel technologies in general. But these novel technologies are actually posing new challenges because we have different new systems like lithium batteries, electric motors, fuel cells with hydrogen, so the way you store hydrogen creates new challenges. Human-machine interface, as we will see later, poses also new sort of environment for the pilots. So how would the pilot react to certain emergencies, certain failures? So also operations with like urban air mobility or unmanned aircraft that are emerging. So does the, let's say, standard approach to safety assessment work also with this innovation, or do we need to maybe develop something new? So the real answer is maybe. I mean, we still, there are open points on this. Definitely, what we have seen from experience is that novel technologies are rather complex, I would say. There's a lot of interconnectivity between aircraft and systems. They, most of the times, there are single systems that perform multiple functions. So in this case, the FHA, so the very beginning of the safety assessment, sometimes can become a bit confusing because it's very hard to understand, okay, which is the function of a specific system, what is the effect of a failure, because it could impact maybe a lot of other systems. So it is doable, but it creates a bit of complexity and confusion. So moreover, there are definitely new failure modes that must be understood, and so maybe it takes, I mean, you discover a new failure mode when you are almost at the end of the assessment and you have to start everything from scratch again. There's definitely lack of reliability data of these novel technologies. So when you have to actually to show that you meet the quantitative safety requirements, there's no reliability data available on databases or on the work, on the experience, on the field. So sometimes it's not very easy to actually show numerically that you meet the requirements in terms of probability of failure. And in general, also for aircraft where software was not used in history, so for like small aviation, general aviation, the software is indeed becoming crucial also for these types of aircraft. So these are more or less the challenges that novel technologies are bringing into the game, and maybe we have to change a bit the approach to this assessment. So there are theories, there are ways to perform an assessment in a different way, and the real need here is really to see the system as a whole. So we have to use the system theory that is used in many other, let's say, environments, and try to see the system as a whole, not with different and specific components that do not have a lot of interactions between them, because as I said previously, there's a lot of interconnectivity in this new aircraft. So we have to deal with the so-called emergent properties. These are properties that arise from complex interactions again, and basically it's how these components and systems interact. So I will stress it out a lot of times, this interaction between components and systems, because it's something quite peculiar of these novel technologies. And studying these properties, so studying how everything interacts, then enables us to identify the new safety constraints. So basically, in short, it has the traditional approach was to prevent failures, so the safety was treated as a reliability problem, and now we have to enforce safety constraints by actually controlling the problem. So we have to treat safety as a control problem. This is summarized by a theory, so it's a system theoretic process analysis, STPA, which is currently starting to be introduced slowly in the aviation sector. It's something that was already used in the past on different environments, and it is something that could actually help manufacturers or also agencies or authorities to discover more and more actually safety issues than the standard approaches, and could actually help to really identify the real safety cases, so not forgetting anything from the complex interactions that arise from these novel technologies. I will not go into detail of this STPA process because that's not the purpose of the meeting, but I wanted a bit just to launch the hint, I mean the idea in this of these novel technologies, of this novel approach. So I think these 2 points could be points for discussion for the workshop. So one thing I didn't mention is that these novel technologies bring together with them also other non-flying systems like chargers, or how to refuel hydrogen, how to refill, so how the refueling station has to be done. So everything that is not flying normally is not considered in the safety assessment process, at least in aircraft certification. So it's considered a bit differently. How would these novel things be considered in the future? So can it still be like now that they are, let's say, qualified completely in a different way, or maybe there should be something different? I don't know. It's something to discuss. And also these novel approaches, so like the STPA I mentioned, from a certification perspective, would the authorities accept something that was not, let's say, in the tradition, or maybe it's a no-go from the beginning, so we shouldn't even start thinking. Things are already moving on that direction, so I'm quite positive on this. But still, I think it could be an interesting topic for discussion. That's it. I was quite short, probably, but I think it's better to discuss than to listen me. So thanks for your attention, and let's see later with the discussion. Thanks.
Thank you very much, Fabrizio. Yes, we are a little ahead of time, so if there is any question from the audience, we may profit from a direct question and answer session. I see a question from one of our online guests. Do you cascade all the way, or do you already have? Oh, sorry. This is a question not on the technical side. Oh yes. Okay. Yeah, it's about the V diagram, I think. So I'm reading the question. Do you cascade all the way, or do you already have links between the two branches of the V in the diagram that you showed? Yeah.
I think this works, yes. So there is, I think, a difference between the theory and the practical world. So in theory, you should actually follow the V. So you start from the top, you go down. So you budgeted the probabilities of each system or components, depending where you are, and then you actually create requirements for your design, and then you start with the design, and then once you have it, you actually check if the real system actually meets the requirements. In practical world, I think it's quite rare that you do a safety assessment when nothing is already done. So probably you start with let's say the up left part of the V, and then you check already in the real system that probably you already have as a prototype or whatever, like something on the bench, on the test. You already check on the real components. So you are also able to populate your assessments, so your fault trees, basically, with real data that probably you already have in-house. So it's always moving left, right, up, down. Unluckily, safety is not objective, but luckily it is very subjective. So there are no standard ways, but yeah, you have to be a bit, let's say, smart to find the best solution, the most efficient solution, not to waste a lot of time also.
It seems that coupling is the word here. So it's present in the design, in the architecture, but also in the safety assessment. You have to always take account of interactions all the time. So not necessarily a linear process in this sense.
No, just another thing. No, there's nothing linear. Also, what we have seen with MAHEPA, we have done the safety assessment. It's really nothing linear. It's you can spend, I think, 4 years just on the safety assessment of MAHEPA, like the entire duration of the project. At a certain point, you have to stop because otherwise you will never reach an end. But it is quite clear from MAHEPA and also other experience that these novel technologies are bringing new problems that will be solved, but currently, of course, as any new problem, it takes a bit of more effort. Nothing is standardized, so you have to think even more out of the box when doing these assessments that already require a bit of out-of-the-box mentality. Because, as I said, pilots' reaction on failures are different. They don't know how an electric aircraft or a hybrid aircraft work, so you have to make assumptions that might be totally wrong. So it's not linear, definitely.
Thank you very much. Maybe we can also answer to another guest, Vincent. Thank you very much, Linda, for your question. And now we have a couple of minutes before starting for the next panel. We can maybe answer to Vincent, asking, does the hybrid concept introduce new safety advantages compared to a conventional single-engine aircraft?
Well, yes. In principle, yes. Then you have also always to verify this. But the MAHEPA powertrains, actually, it's any hybrid system has let's say, a natural redundancy in itself. Then you have to see with common cause analysis if this redundancy is really there. But let's say the architecture itself allows for much easier way to create a redundancy there, because of course if you have a internal combustion engine failure in a normal aircraft, there's no power anymore, while here in Pantera, for example, you still have the batteries, so there are more safety margins, let's say. So MAHEPA actually developed the systems always thinking about safety. Also the electric drive is composed by two motors in one single case. So these two motors are connected through a freewheel that in case of a single motor failure, the remaining one can still spin the propeller. So yeah, hybrids in general, as in the design phase for aircraft design, they create a bit of more freedom to how you put things around the aircraft. The same also for safety. So there are multiple ways to meet the requirement.
That's very interesting, because complexity is somehow paying in giving more chances to get higher reliability, as in the MAHEPA case. We have a higher reliability than a single-engine aircraft in the end. Thank you very much. So it's time to give the floor to our second panelist, Dr. Fabrizio Oliviero from Technical University Delft. The title of his speech is Innovative and Safe Hybrid Electric Architectures. Please, Fabrizio.
So good afternoon, and thank you for an introduction. Well, I have to say that despite of the same name and despite of the same nationality, I'm not a safety engineer. I'm actually a researcher and lecturer, and my background is about aircraft design, and aircraft design into the academia. That is pretty different because usually in the academia we are focused more on performing design activities, try to look at more fundamental research, to answer to more fundamental research questions, and it seems at the first sight that we are not directly linked to safety aspect or safety evaluation of a certain configuration. But we actually do that in a sort of indirect way. So as a small, let's say, disclaimer for the presentation of the next slide, I will not talk in detail about what is safe or how to make a certain vehicle safe, but I will try just to raise some, to identify some critical point that all of us as a engineering community has to bring forward in order to make such an innovative configuration and such an innovative solution possible and really flyable in the future. Then actually, I would like to really briefly talk about two small different aspects of safety. The first one is related about what is a safety approach during the early design stages when designing innovative aircraft featuring either hybrid powertrain or even having more, let's say, exotic configuration like distributed propulsion or ducted fan featuring, let's say, complex aeropropulsive interaction. And the second aspect is related actually to the estimation of performance of such a vehicle, how to save and what is the consequences in terms of safety to determine correct performance parameter for such vehicles. Regarding the first point, what is, let's say, from a design perspective, what kind of challenges hybrid configuration is bringing? From a purely design perspective, hybrid architecture are bringing a new way to design a vehicle, in my opinion, because basically there are more parameters to be included during the design process, meaning that our design space is increasing, the number of variables are increasing, the number of type of constraints are increasing. And on the other side, we have also to tackle possible innovative aeropropulsive interaction that can enhance dramatically the flight performance of such vehicles. And we have to take into account how safe they are, how possible is really to implement those kind of solution into a feasible airframe. And just to understand what we are talking about during the early design stages when dealing with a complex, let's say, hybrid propulsion configuration, such the one that is now reported in the slide, we can have really an increased number of components in the overall powertrain. Perhaps some of these devices can be less complex in the design with respect to a normal conventional turbofan, but we have an increasing number and a complex linkage between all of them. And therefore, in order to design all the components and also the airframe itself, according to the different requirements, then we have to introduce new parameters. That can be just, for instance, can be the hybridization factor, so how much is the power coming from the battery with respect to the total power coming from the other power sources. How much is, let's say, how I'm controlling the throttle of this complex system is also not so trivial to understand. And usually during the early design stages, we have to determine what happens is we have flying during a critical configuration. And then the first question arises, what is here a critical configuration? And it is not a straightforward answer for this question. It's actually very case specific. And we have to really try to give an answer step by step and configuration by configuration. Actually, in this case, one engine operative case is not actually something that is immediately conceivable, because we have multiple devices, so it can be something that is not really the critical configuration that we have to take into account. But then, what we can deal with is actually the so-called critical thrust loss, and something actually that changed in the last year in the regulation. It was quite an important change from design perspective, and it's opening a totally different way to design an aircraft at early design stages, actually. Okay, I will try to be very brief here, but I will try to let's say, act as a lecturer, since also lecturer is one of my job. And I will try to give you an idea of what is, how important is a critical thrust loss during the early design stages. Usually this one is the performance constraint diagram of an aircraft. That is usually something that has to be plotted in as early as possible during the design stage. And it allows us to determine the wing loading and the thrust loading or the power loading of an aircraft. So we consider all the flight segment for a nominal mission. We consider also critical condition, and then we identify a sort of feasible region for those parameters, and then we usually select the best point inside this region. Classical engineering exercise that we teach to our aerospace students, and usually the conventional design is intended to find the best point that usually lies as right as possible in this graph and as high as possible. This is to minimize the dimension of the wing and to minimize the dimension of our propulsive component powertrain. The question is, how does this diagram change when considering in operative condition for such a complex powertrain? Well, the question is yes, in multiple ways. And the first one is that basically we have a lot of multiple conditions to be considered. Now I just would like you to consider just how many solid lines are present in the diagram on the right part, in which basically we are increasing the number of conditions to be considered, and each one basically it's related to the failing of a certain component inside the powertrain. We don't know a priori which is the most critical condition for such a complex powertrain when you have power branches coming, providing different percentage of power. So we have to specify step by step what happens to the performance of the aircraft when having a certain critical condition for a certain component, and when we have to repeat this exercise for all the components. So the determination of this diagram can be a little bit more complicated. It is actually not enough, because we don't have just one diagram when dealing with hybrid power branch in which you split the power. But we can actually, the way we defined our design approach at TU Delft is actually to plot different of those diagrams for the different power branches of an hybrid powertrain, so that actually the sizing point for the batteries can be totally different from the sizing point of the thermal engine if you have a serial hybrid configuration. Or also in the case of a fuel cell, again coupled with batteries, also the sizing condition for the fuel cell can be totally different from the one for the batteries. And therefore, there is another point that the critical condition can affect the design really at component level. So we start at looking the powertrain as a whole, but then we have to go back step by step to see what is the condition that is sizing either the batteries or the electric motor or the power generation system, etc., etc. And again, it is very case specific depending on the type of requirements that are applied to the aircraft and on the type of architecture and the type of components. Since we are not happy in having so classical hybrid configuration, we are also dealing with innovative aeropropulsive interactions. And this is fundamental. This is fundamental because electric components are opening us a new world, because compactness, lightness, and easiness of installation of such components allow us to exploit, let's say, to locate the propulsor in several positions along the airframe in order to exploit several physics-based phenomena. Just to give you an idea, here we can deal with leading gauge distributed propulsion in the left part, or also boundary layer ingestion located at the aft part of the tail cone, or wingtip propeller, or ducted fan, again located at the back of the fuselage. All of these, let's say, type of innovative solution are really aimed at enhance either propeller performance. For instance, when locating, when dealing with the boundary layer ingestion on wingtip propeller, we can, let's say, enhance the propulsive efficiency of our thrust devices, or we can use such devices to enhance the characteristic of the airframe. Distributed propulsion is really a powerful tool to increase the lift coefficient at low speed, for instance. Or we can use them to arrive to a solution that is lighter. Or again, we have to deal also with a solution that have to favor, for instance, noise reduction or less vibration. And it is the case, for instance, of ducted fans located at the back of the fuselage. So there are a lot of, let's say, phenomena to take into account, a lot of different purposes that can, let's say, dictate the preference of a certain solution with respect to another one. And of course, it means that at early design stages, we have to cope with a very complex phenomena. And therefore, the sizing in this case is also quite complicated. Just to give you a very rough example, in the case of a distributed propulsion airframe, it means that in this case, since the presence of the propeller along the wingspan of an aircraft have the effect to increase locally the velocity and also the incident that part of the aircraft is feeling, it means that the lift coefficient of the certain aircraft is actually linked to the thrust coefficient of the propeller. And the drag coefficient is actually linked also to the thrust coefficient. Of course, this is not intended today to talk about the models that allow us to have a preliminary calculation and a preliminary sizing. We validated them for possibly with experimental tests. But the overall idea, again, if we look to a relatively simple but very useful instrument that is, again, the performance constraint diagram, is that when using distributed propulsion, I can increase the lift coefficient at low speed, meaning that in order to achieve low speed characteristic and be able to land to a certain airfield, I can reduce the size of my wing. Usually by 15–20%. But again, from safety perspective, there is a sort of different approach, because then someone could argue, okay, but from safety, what happens to the lift coefficient if there is a certain critical condition in which part of the powertrain is switched off? So that basically the part of the lift coefficient that we calculated at the nominal condition is actually not met. So from one side, the design would like to really exploit this aeropropulsive interaction, but from the other side, safety would like to maintain the worst case scenario in which, for instance, in this case, the part of the CL related to the CT should be 0. And again, where the compromise is something that is an open question. Again, a possible approach is that actually we determine what are the safety requirements at component level to make this kind of devices possible and to really exploit this kind of interaction. Again, just to put numbers of some of the ideas, this is a type of innovative hybrid serial electric serial powertrain featuring 10 distributed propulsion propeller along the wingspan for a 19-passenger commuter that is compliant in principle with all the CS23 regulation of today. So we look at the safety from a regulation perspective, but again, in this case, no effect of critical inoperative condition on the lift generation is considered. So perhaps the number that are reported in this slide should be a little bit worse in order to make this solution a little bit safe or safer. Last but not least, we are calculating performance, and the performance in the case of a hybrid propulsion powertrain, of a hybrid powertrain, is also linked to this control parameter. Just again to give an idea of a study related to a regional transport aircraft, ATR 72-600 benchmark. The usual type of mission parameter that we have to consider, for instance, are the rate of climb that usually is identified just in part of the climb that is determined by regulation, but then it's up to the user to define what is the best rate of climb. And for the conventional case, that is determined, and we run some sensitivity analysis of what is the overall configuration, in this case expressed in maximum takeoff weight at varying this parameter. And in this case, you see that at varying rate of climb for a conventional aircraft, as an input for the design, the overall design in terms of maximum takeoff weight doesn't change so much. In case of applying the sensitivity studies for a serial hybrid configuration, the story changed completely. The sensitivities at this average rate of climb is really a lot, meaning that when changing this rate of climb by 20%, more or less the maximum takeoff weight is varying about 10%. That is quite a lot. It's making quite a dramatic difference in the overall design. And even more dramatic is the dependence of the maximum takeoff weight with respect to this hybrid control parameter. For instance, namely, how much percentage of the power to perform the climb is, for instance, coming from the battery or from the thermal part of the engine. In this case, really the dependence of the maximum takeoff weight is really dramatic. And from one side, again, the designer would like to propose the best configuration possible, meaning maybe having identify optimal point, but on the other side, safety imposes a certain flexibility, a certain off-design condition that have to be, that the aircraft should be capable to fly. And again, this kind of compromise is very difficult to find when the sensitivity to those parameters is studied, is involved, is applied for a hybrid powertrain aircraft. It is not only important for the design, in my opinion, but it is also important for in-flight performance, because this is a study that, a sort of activities that we perform for a former project of MAHEPA, the project Hipster, in which basically we try to determine what are the performance of a certain hybrid aircraft, again featuring serial hybrid configuration. And in the slide now you can see the HMI of this aircraft that has been proposed by this aircraft, in which basically the pilot could read two basic information: the amount of the remaining batteries, the state of charge of the batteries, and the remaining flight time. So the question is the remaining flight time sufficient data to perform a safe flight? In my opinion, no, because then it gives the idea of how much energy is stored on board, but it doesn't give the idea on what kind of high power maneuver the aircraft can perform. So that the other question related to performance is how, let's say, what kind of performance need to be calculated and to be given to the pilot in order to have a safe forecast of what is the remaining capabilities of the aircraft, of the flight characteristic of the aircraft. We proposed a possible approach that is basically consisting in using a sort of simulator to estimate in real time the remaining performance of the aircraft. Again, the mathematics and then the engineering approach that is behind this simulator is pretty complicated. It's not the idea of this talk to talk about this, but again, there are critical aspects when dealing with this. How the numerical calculation and the numerical error is affecting the evaluation of the performance, and how the error, the error coming from the sensor that should read the initial status of the aircraft are, let's say, propagating when estimating the performance. And again, this is not, let's say, an open question that should be addressed in future research activities. So in conclusion, from a design perspective, hybrid powertrain aircraft really represent a very interesting and exciting challenge for a designer, because we have to deal with really new design space. And new design space also brings new approaches into designing. And in this, let's say, context, identify what are the critical conditions in order to guarantee a safe configuration. They are not so trivial to be determined. In this context also, performance estimation is playing a critical role, and they should be really considered very carefully during, in my opinion, the initial design aspect of the aircraft, and also during the execution of a real flight. Okay, that's all from my side. I hope that I gave you a nice overview of what are, let's say, our approaches on safety during the design stages, and I'm really open for every kind of question. Thank you.
Thank you very much, Fabrizio. So I see a question posed, but I'd like to postpone this to the panel discussion just after the next intervention, so that we can keep in line with the timeline of this event. So I'd like to ask Dr. Sumantra Bhattacharya from Ulm University to take the floor with his talk about integrating new concepts in safety, reliability, and efficiency. Sumantra, can you confirm you can hear us?
Yes, I can hear you.
Great. So thank you very much. Welcome, and the floor is yours.
Thank you. So welcome to the presentation. My presentation topic is integrating new concept in safety, reliability, and efficiency. My name is Sumantra Bhattacharya. I am a researcher at Ulm University, and my research mainly focuses on power electronics. So in my research, I generally look into different aspects of power electronics, for example, DC-DC converters, and how we can integrate them into the drivetrain of full electric aircrafts, and also look into different aspects of safety, reliability, and efficiency. So as a university, we also focus heavily on the research aspect. We have actually done a lot of research on DC-DC converters. We will talk about them. And in this presentation, we will we will show you a DC-DC converter that we developed at University Ulm that is highly efficient, as well as has different functionality that can be named as fault tolerance, which can be integrated into the future aircrafts as a DC-DC converter. I have outlined our presentation in such a way that we'll first talk about which converter I'm talking about, how the operation modes are, and I will show you that hardware that's developed by us, and we will draw a conclusion afterwards. Good. Before we start, just talk about the motivation behind our work. So as our previous presenters told, like there is a growing trend in the aerospace industry to electrify everything. So there is a trend that we have to replace all the mechanical or pneumatic properties or any engines by everything by electric components. And this drive is also known as More Electric Aircraft Initiative. So what we're trying to do, we are trying to develop high power density, for example, using silicon carbide switches and high efficiency DC-DC converters. For example, if you take a look at the architecture that's defined by More Electric Aircraft idea, we can have a fuel cell or a battery, for example, as a power source. And this battery or fuel cell will give you some voltage, and this will be converted to some different voltages, which is by definition it's plus minus 270 volt, which is 540 volts DC. Then we can connect the inverter to drive a AC load, for example, our propeller, and we can further derive this voltage to another 28 volt, which will be now connected to a cooling system and sensors. This can be 28 volt. In our case, it's 24 volts. So as you can see, in order to make electric aircraft work, the future is we have to talk about the heart of the aircraft, which is the DC-DC converters. Without efficient and highly powered DC-DC converters, the concept fails. So okay, DC-DC converters are a good idea, but it's there in automotive industry. So what's different in aviation? In aviation, the biggest problem is the reliability. So once we are flying with DC-DC converter, we have to make sure if there is some situation or some problems, this DC-DC converters should be able to hold or have to perform in a way that the aircraft doesn't lose its power. So there are different aspects of that. For example, to increase the reliability, there are topologies. For example, you can put more than one DC-DC converters in parallel as like redundancy. Or we can put, for example, if you take up to this DC-DC converter, we can put a bulky battery bank as a parallel as a redundancy. Well, this sounds good, but this all adds up to the cost, weight of the whole aircraft. And to reduce the weight of which we saw in the previous slide, that to reduce the weight of the aircraft is very important. So we were looking into different aspects, and we were looking into possibilities to make our converter more reliable. So first thing we did, we used silicon carbide switches, because silicon carbide has a very positive effect on the weight and the switching frequency of the converter, because silicon carbide switches, which is the biggest, hottest research topic at the moment in the field of power electronics, can be operated at higher frequency. As a result, we can bring down the cost as well as the size of the magnetics. And also, we looked into like different parameters of inside a DC-DC converter that are prone to failure. So in a DC-DC converter, there are several components like capacitors, inductors, transformers, etc. But we saw some of our research that the semiconductors are the most common sources of the fault in the converter. And when a fault inside the silicon carbide switch happens, or a power diode happens, it normally assumes a short circuit or this open circuit position. So we tried to develop a new topology for our application that can reconfigure in a multiple ways, so that if any switch becomes suddenly faulty during operation, the converter will reconfigure in such a way that it will remain its output power. And I will show you how we did that. So how a typical DC-DC converter looks like inside a aircraft is something like this. So this is a very old topology, it's nothing new. So we have a transformer to galvanically isolate the input and the output side, so that if something happens on the output side, we have a natural electrical barrier between output and input. So what we do, we put a DC voltage on the input and we switch it in a complementary fashion so that we get a square wave, it's the AC signal. Then we have resonance tank, and then we put a transformer to scale up or down the voltage, and then we rectify it to get a DC voltage. So first thing we did with this converter to optimize it, we turned into the silicon carbides. This is a diagram that we see from the silicon carbide switches from Rome Semiconductor. What we saw that by using silicon carbide, we could easily go for smaller cooling system. This can withstand higher temperatures. We can go for very high frequencies. So as a result, what happened by incorporating these switches into silicon carbide switches, we saw our efficiency went up because we could go for higher switching and easily soft switching parameters. Also, we saw that we have decreased the size of the magnetics. For example, this inductor, this transformer, the size went very small. Yeah, so this was integrated. So we have, by that, we increased efficiency a lot. Then what we did, we tried to look into the fault tolerant properties. So we set up a few goals before we started our research. Our goal was to develop a new fault tolerant topology. So as I mentioned earlier, our goal is to ability to take a faulty diode or a switch offline, completely out of service. And converter must maintain our nominal voltage and current at all time. So this is how the modification we did that I highlighted here. So we changed the transformer into a 3-winding transformer. We added a couple of switches and a diode in parallel, and we broke the capacitor instead of one to a split capacitor. Small example, what can this converter do? For example, let's say we are flying and suddenly this silicon carbide switch Q3 becomes short-circuited. So what happens in that case? Well, we will see this is a short-circuit path and we cannot control it. As a result, our output voltage becomes garbage. We have like very faulty performance. Our output voltage goes down, our current goes down, etc. And because high current flowing through it, the switch gets burned as well. So we thought, okay, if this switch is faulty, let's say, can we use this switch somewhere? So this is a closed path. So what we did instead, we made an algorithm. So we have a technology that detects these faults. And at the same time, what we do, we open this switch. Now what will happen, this full bridge kind of configuration becomes a half bridge converter where we have this path integrated into the whole system. Now the voltage will become half because now we don't have a force switch instead of two switches operating at a tandem fashion. So what we need to do, we need to reconfigure the secondary side where the switches that I put into on the secondary side comes into action. This is, for example, 2 modes of operation. One configuration strategy, for example, we have taken this as a short circuit path and this switch is completely off. And we turn on these 2 switches. So what happens is now a different pair of diodes are working. And transformer is, there are 2 windings of the transformer which are energized simultaneously. So as I mentioned earlier, the problem with the half voltage that we were having before, because transformer now both windings are energized, what will happen, this will double the voltage again. And as a result, then we have the similar diode bridge that is rectifying the whole voltage, and we will have the output voltage and power maintained all the time. Interesting to see here that this can be also used when, for example, we see a fault in diode D3 or D4. So on this side, if you see one switch is suddenly damaged, we can use it, you can reconfigure it in this way so that we can take off this D3 and D4 completely, so they are not taking part in the rectification circuit, and we will still have our output voltages maintained all the time. So this is one strategy. There are different strategies that we saw. This is the beauty of this topology. For example, let's say we have diode D3, D4, D5, D6, any one of them is like damaged. We can have the similar concept that we did. We deconfigured the primary side, and we can turn on different set of switches. Here, what we did here, the capacitors are important because what we did with the capacitor, the transformer is not doubling the voltage, right? So in order to double the voltage at the output, what we did, we used a capacitive voltage doubler here. So what happens during one cycle, this capacitor gets charged, and during the other cycle, this capacitor gets charged. As a result, what happens, like this two capacitor charged to half of the voltage. Together, we had the complete voltage, that is the nominal voltage that we were expecting at the output. So as a result, this is the strategy 2. There are different strategies we can include. So this is a highly flexible one because any switch, any diode, if we see a problem, we can take it out and we can reconfigure this switch in a way that converter will, under any circumstances, provide you output voltage, power, so that we have no problem whatsoever. Okay, for example, we did some simulation before we put into the work. For example, let's say we simulated here, there's a fault in the switch and the switch is like continuously on, for example. And we had some control algorithm which takes time to detect this fault. As a result, we see the output voltage, for example, was 28 volts and it dropped to some 20 volt value, which is the fault situation. And then we did the reconfiguration here, for example. And as a result, the voltage slowly recovers to the original voltage. Also, the current recovers to the original nominal value. We also included some extra algorithms called root locus tracking and soft switching, so that this transition is very smooth. We don't have a very huge spike, so that we don't damage anything connected to the output side. So this is the hardware that we developed at Ulm. So this is a 540 to 28 volt DC-DC converter, which can supply 120 amps at full load condition. So as you can see, the transformer, this is dimension of this is 30 centimeter by 23 centimeter, which is a very small. We have compared this product with actually some industrial examples that we used for our MAHEPA project, for example, the 24 volt DC-DC converter, and the weight and dimension is pretty much similar to those, even smaller than some of the solutions that we got. And what we did, we also incorporated 2 additional DC-DC converter here, which can give you 5 volt and 12 volt. So in case our sensors, there are different sensors which needs 5 volt and 12 volt. So for example, for that, we need another DC-DC converter or another small circuit for that. To reduce the space requirement or the weight, we integrated everything into this circuit. So we can take 28 volt, 12 volt, and 5 volt at out. Also, this is a very different architecture, different power circuit for us, because normally, if we are talking about 120, 150 amperes of current, we don't normally use like a copper bars or copper bus bars. So we connected with a couple of manufacturers in Germany, and they designed a PCB for us, which has a 0.5 millimeter copper as tracks, for example. You see these copper tracks are really thick copper tracks. So everything is now integrated into one PCB. So this PCB has, you don't need extra copper bars, so you don't need extra connectors, you don't need extra screws and bolts, for example, which are often problematic during maintenance and etc. So everything is integrated into one connector. So that's how we reduce the number of components. We have made it compact, and we have tried to make sure the weight is also minimized. Also, you can see the transformer here. So this is a very small transformer. This is a 3.3 kilowatt transformer with 540 volts. You can see the size of the transformer and the inductor. So this is the beauty of using silicon carbide switches. We can drastically reduce the size of the inductor and the transformer. And we actually did the measurement at full load, 3.3 kilowatts. And our silicon carbides, because of the soft switching, they didn't get hot at all. So in our case, these switches are not cooled at all. So they're just hanging without any cooling. So we don't need to cool the switches. So this is a beautiful aspect for us that we achieved with our high soft switching frequencies. So what are the further development that we are working on at the moment is one of the problem with silicon carbide is the detection technique with IGBT that is there for centuries in our market. We have properly established technique to detect a fault very quickly. With silicon carbide, it gets a little bit tricky. So we are working on it to detect techniques to detect fault in silicon carbide little bit faster. We had trying to develop control algorithms. So we are investing a lot of time to develop the embedded system programming for the whole controller so that we can detect the fault and take action and also cover all fault situations that can be occurred during the operation. We are also trying to research on the cooling optimization. So because this converter that I showed you was air cooled, if you replace it by water cooling, for example, we can reduce the weight another by factor of 30% or 40%. So it's a very challenging task for us. We are trying to incorporate that into our next prototype. Another problem we have at the moment is the EMC issues. So EMC, because of the high frequency, we have a lot of EMC issues. So we are trying to design our converter in a way that it will pass all the EMC criteria, which is a crucial part of the aircraft design. And our last step that we are currently working on because at some point we want to go for certification of this converter, we want to have environmental and mechanical test and in a climate chamber done. So we are trying to design our converter that it will satisfy DO 160 environmental condition and all the criteria laid down by, for example, military standard 704 for DC-DC converters. So that's our plan. So we want to go further, design a converter that we can be a product in the market in future. So to conclude, we developed a fault-tolerant resonance converter topology. I discussed some operation mode and configuration strategies. We incorporated silicon carbide to increase reliability, efficiency, reduce weight. We developed a hardware, for example, to show that our concept works, and we are trying to bring it to the certification so that we can put it in the market in future. So the proposed converter is ideally suited for future electric aircraft. We can replace this with our present 24-volt DC-DC converter, and at that we can make the converter more reliable, flexible, and we don't need a bulky external battery, so we can save a lot of weight inside the aircraft. So thank you for listening. I'm looking forward to questions later. Thank you very much.
Thank you, Sumantra. Thank you very much for this detailed presentation, highlighting how safety should be considered from the very components at the core of these new hybrid electric powertrains. Of course, electrical machines are becoming more and more important, electrical components, so that's a clear demonstration of how research can actually fit into this new trend towards a new era in aviation, as we like to say. Okay, so we are basically in time to start the panel discussion. I'd like to propose to our speakers a few questions that have been posed on the chat on the YouTube channel, but I'm also enticing questions from the audience in our conference room, if any. So first, I'm reading a question from Berkan. What kind of fail-safe system do you introduce in single-engine aircraft powertrain? So this is definitely pointing one of the most important aspects that was discussed previously. So single engine is no more a complete definition for these new powertrains, because the idea that you have a single engine as in a traditional aircraft is now substituted by a plurality of sources that can be combined in several different ways. As Fabrizio Oliviero showed us, there is a great enlargement of the design configuration from this point of view. But of course, in MAHEPA, we have achieved, during the consortium work in the past 4 years, we have achieved two extraordinary milestones, because we have two flying aircraft, one with a fuel cell hybrid system with batteries, and another one with a thermal hybrid electric serial propulsion architecture, that are actually not single engine, but are single propeller. So in the end, there is a single, let's say, actuator to the propeller. So maybe we can start from this point of view. So Fabrizio Gaspari.
Yes, you said it correctly. Basically, it's a single propeller, it's a twin engine single propeller configuration, because as I said, I briefly mentioned, the drive itself, it's composed by two different motors that are connected via a freewheel that enables the operation of a single motor in case one is down, let's say, or is off. But then there is also the same criteria more or less in the inverters, because we have two inverters, so in case one goes down, then the other one can still provide enough power to go home. And almost the same principle applies also to the batteries, because we have two batteries in a parallel configuration in each battery, so in each wing. So also there, if you want, there's a redundancy or a fail-safe criteria, principle. So again, as I said before, and as the other Fabrizio said, in the design phase, but also in the integration phase, hybrid technology allows for more freedom. So it's definitely easier to put two electric motors on a single shaft than two internal combustion engines on a single shaft. So. Sure. Yeah, this allows for more freedom to play, let's say.
Sure. And the whole concept of modularity, which is central to MAHEPA, is also an important element, because we can couple these basic elements, such as single electric motors in this configuration that you described, also in larger size aircraft applications, such as the configurations that Fabrizio Oliviero mentioned. So we may have several different thrusting units propelled, actuated by a plurality of electric motors clutched in this way. So this definitely opens the stage to a much enlarged configuration from a safety point of view.
Yeah, just a comment. I would like to point out that this does not mean that every hybrid powertrain is naturally safer. I mean, sure. It gives you more freedom, but then, as I pointed out in one slide, there's also always this monster that is the common cause analysis. So you have to understand if these, let's say, fail-safe principles or redundancies are really redundant, because complexity increases, so also the possible common failures actually increase. So it gives you more freedom, but also you have to be quite careful to consider all these aspects, just as a note.
Sure. Thank you very much. So we have another question from Dominique. I think Fabrizio Oliviero may be the right person. Is there a paper or other information available on the remaining electric range simulator?
Can you repeat?
A remaining electric range simulator. So the simulator which allows to evaluate what is the electric range, the full pure electric range in case of a failure.
So yes, there is. Yes, there are there is some literature available. Maybe later on I can try to reply in the chat, or maybe he can contact me. Of course, there are studies going on, so we also would like to publish the latest findings. If I may anticipate a little bit, the problem is really on numerical resolution in that case, because it's really for a real-life application, achieving, let's say, solution that have a relatively low error is paramount. And of course, when having such a complicated problem to be solved from a numerical point of view, the robustness of the numerical setting is questionable, but of course, as an engineer, we are thoroughly working about regarding that. And the other question, and the other part, as I was anticipating during the last part of the presentation, is also related to how to couple this possible simulator on board an aircraft, for instance, in the future, with the other part of the system. This kind of analysis requires information that coming from, let's say, the actual status of the aircraft, so altitude, speed, such information, and also information related to the actual status of the component. And again, having a number of sensors means that those sensors can have an inner error that is propagating during the calculation. And again, this is something that has to be taken into account in order to make this kind of approach feasible. It might be maybe not the best approach, it might be one of the possible approach, but of course, when try to solve this problem, those kind of aspects should be taken into account.
Thank you very much. In this connection, I'd like to point out to our guests that we have a website, www.mahepa.eu, which is not only a pretty active website with lots of information and news, but also a point of reference for some scientific information related to the outcomes of our project. So, for example, you can go in the results section and you will find a number of public deliverables. So some of the outcomes of this project are publicly available. You can look not only at the results themselves, but also at the vast literature that is reported in these documents. And I'd like to mention that as a project, we also have been pretty active in disseminating with the scientific literature. We have already more than 20 publications in journals and scientific conferences, and we will have more in the next months as, of course, the maturation of our results will allow us to provide more evidence of our research. So don't hesitate to get into contact through the website, www.mahepa.eu, to get contact with the researchers involved with the consortium, so that we can point you out to relevant publications of interest. Okay, so that said, I see another question from Yasir now. I think this is directed to Sumantra. The question is, could you please elaborate what are the electrical losses in a galvanic isolated converter? For example, in terms of percentage of how much energy or power is lost. Thank you very much.
That's an interesting question. So amount of power is lost depends on a couple of parameters. For example, let's say you are designing a converter which is from high voltage to high voltage. In that case, our efficiency is around 95 to 98%, depending on how much current you are taking. If you are going for the converter that we just showed you, it's a high current converter, low voltage, for example, and in that case, we have efficiency around 92% at 120 ampere. So in that, 8% energy is lost in thermal waste, among which my research says it's 6% at the diodes, 2% at the transformer, and the rest is in MOSFETs.
Thank you very much. Any other questions? Please, so we have a question from Alberto here in the conference room. You may get the microphone and pose the question directly. Thanks.
Thank you. Can you hear me?
Yes, sure.
I would like to ask if you can make an example of a kind of internet cross failure that cannot be detected with a standard method that could be detected with new approaches.
So Fabrizio Gaspari is answering.
This is a very interesting question that we could stay here for like 3 or 4 hours discussing about these things. So I actually don't know how to answer properly. I just know that there are data that are showing that this novel approach, either in design for safety, but also in like accidents investigations or incident investigations, data shows that I think more than 30 or 40% more of of like failure issues or safety constraints, also in these cases, were identified with this approach. Also, the interesting part is that these data were actually analyzed by a young engineer, let's say. So they tested it, and they put a very young engineer just went out from the university approach. I mean, he did the approach with this assessment, and basically he discovered more issues than what senior engineers discovered with the traditional method. So it's a new thing. Also, personally, we are starting utilizing this on Pipistrel, at Pipistrel, just as a, let's say, internal research activity. Because we believe that it would help a lot the future assessments, because we have seen from experience in certification also, standard approaches are fine, but really they require a lot of brainstorming, of course, as always, but there's the risk of forgetting some links. And this would then require a complete reassessment, waste of time, money, and everything. So we have seen from other conferences and examples of these novel approaches that it is a possible, let's say, it could improve the analysis and get better results with also less time. So we believe it's worth to try, let's say.
Definitely. Thank you. Any more questions? So I don't see questions posed online. I'd like to go back to Fabrizio Oliviero about his fascinating presentation about the diversity that can be encountered in designing a new airplane with these new technologies and the opening of new architectures. You've touched about several aspects, performance and architecture. What, in your experience, also through the MAHEPA project, what is, in your opinion, the most critical aspect from the point of view of safety? If you could sort out something that is of absolutely primary importance.
So the question is about determining what is the most critical among the critical aspects. Yes. That I try to determine. I would say that from a design perspective, really the implementation of aeropropulsive interaction, so having a really innovative aeropropulsive solution is really a key element to really enable electric flight, hybrid flight, or electric flight in general, because it's really where we can exploit the advantages of having such small and compact engines. Therefore, I guess that the open point about how to critically tackle the integration of such aeropropulsive integration into the design is really important. For the moment, basically, we are sizing by doing some educated guess on possible, let's say, failure and critical condition, but it's something that have to be really explored further on, and also with the help of certification authority think, because it should be really a brainstorming about also different experience that should allow us to determine what is really the best strategy to implement such new innovative configuration into the airframe.
Thank you very much. I see a new question on the chat by a guest, Pinco Pallino. Italian Italians will definitely have a smile on this placeholder name. What is the safety concept on hydrogen leakages? We didn't talk much about this topic, but we may profit from the presence of Paolo Romagnoli, who is a panelist for the next part of this workshop, and has been heavily involved in flight testing. And as you know, in the MAHEPA project, one of the two new aircraft that were put in flight was the HY4, running on a powertrain that blends fuel cells with hydrogen stored in a pressure vessel and batteries. And so the flight testing has been accomplished here in Slovenia under the responsibility, the co-responsibility of the LR, H2Fly, the other partners of the project, and of course Pipistrel. So maybe Paolo can have a few words about this topic.
Yeah, so definitely safety aspects related to, in our case, gas hydrogen have been, we had obviously to consider them in the design and integration phase. To be noted is that this aircraft was designed to be a flying test bed, so it was always designed and operated in a flight test environment, so in a research and flight test environment. So the safety requirements are, in this case, slightly different than from when you design an aircraft to be operated in a normal operation and to be certified. The main aspects are the ones that probably everyone has in mind. So the containment of the leakages in the tanks and in all the lines, the hydrogen lines, high pressure and low pressure. And how did we tackle that? First of all, from design point of view, and running also ground testing of all the equipment properly, studying the various failure cases of all the components, qualification of components for flying environment and for different operating temperatures and different pressures in the vessels and in the pipelines. And as well as from the pilot perspective, installing sensors, so detecting the presence of hydrogen in the various areas of the airframe where hydrogen is stored or is flowing. And this was then displayed to the pilot with the warning messages on board. And the last safety measure we took for the flight test campaign was to always perform flight testing with the chase plane because the potential flames or let's say hydrogen fire would be invisible from the pilot sitting on one of the two fuselages. So in case the leakage or the fire would happen on the other fuselage, would be invisible to the pilot. So we always flew with the chase plane to detect any hydrogen or fire in general from the chase plane for the pilot. In this case, the pilot would be informed. Obviously, the number of questions and the number of failure modes that will appear at the time you will design an aircraft which is intended to be certified from beginning is definitely wide and in some areas I believe still unexplored, both from the industry and from the certificating authority.
Yes, thank you. Yeah, I would say this is a very hot topic in all, yeah, under all points of view, and very hot also from a political point of view, because the European Union is strongly addressing the usage of hydrogen in transport applications, not only in aviation, of course, starting with land applications. So this is definitely something that will be addressed in the future as one of the main problems, safety in handling and storing, supplying the hydrogen, and keeping control on the hydrogen system. We have a further question from Siska Perek. Did MAHEPA implement any optimal power splitting strategies for the flight demonstrators? So maybe Fabrizio Gaspari may talk about the power splitting, yes.
Yeah, I think actually the other Fabrizio is probably more suitable, but I will introduce it. So, yes, definitely. The advanced power management concept was actually one of the objectives of the project. So having multiple sources of power on board, of course, allow you also to use them in a different way than a conventional aircraft. So especially University of Delft, so I will leave Fabrizio explain a bit the details, developed a model in order to understand which are the most optimal ways to actually use the sources of energy and power that you have on board. It was not trivial, but I would leave the other Fabrizio to explain the details.
Fabrizio Oliviero now.
Yes, yeah, we actually did. It was actually one of the explicit goal in some of the tasks of the work package of the project. The job has been intended really to determine what is the best power management strategies, so a sort of time evolution of how this power management is evolving along different flight phases for a certain aircraft. So basically what we did consisted in, first of all, determining an optimization strategy, and then coupling this optimizer with a simulator in which basically we included all the information coming from, let's say, the efficiency map of all the components, and then we optimized not only the power management, but also some flight trajectory parameters along the certain mission. Again, the outcome were not general, in the sense that there were solutions really differing a lot for from the HY4 till with respect to the Pantera, for instance. But maybe it is the case to raise another point with another question, that is, what is optimal in this case? It's something that I personally not have a complete answer to, in the sense that, of course, at first, optimality would be strictly linked to the minimization of the overall energy along the mission. But it can be only related to the optimization, only the minimization of emissions. And of course, the objective might look similar, but actually they don't, and the solution might differ quite a lot. And again, someone would like to also optimize for time reason, and again, the overall solution changes completely. So we did, and we have proposed an approach that might work, but again, what is important from an engineering perspective is to determine what is really the objective for such an optimization.
Thank you very much. Okay, so we are running a little bit late, but I definitely think that we got interesting questions, so we could touch on several points of interest. I'd like to update now the meeting and have a 10-minute break. So thank you very much, all the guests connected online. We will resume our workshop with the second part dedicated to the HMI considerations, novel cockpit environment, which will deal with how the complexity of these realizations are managed so that a pilot can handle all this in a practical way, which is definitely another fascinating aspect of the implementation of such new technologies. So let's meet again online and in the conference room in 10 minutes at 4:50. Thank you very much. Thanks.
We all wish to live in a clean and safe environment, but due to the increase in high air traffic volumes, our impact on the environment is still increasing. In order to reduce emissions and provide cleaner technologies for future air transportation, a partnership has been formed in 2017, which launched the European-founded project MAHEPA under the Horizon 2020 program. The MAHEPA project is not only developing new key powertrain technologies, but it is also building a roadmap for future market implementation of hybrid electric aircrafts. In the future, when air travel will increase, clean technologies such as the one developed in MAHEPA will help to obtain a safer and cleaner environment and will enable us to travel around the world fast, green, and cheap.
My name is Thomas Koopman. I'm from the Netherlands and I studied in Delft at Technical University. I did aerospace engineering.
My name is Christian. I come from Slovakia.
My name is Vasa Plesec. I'm 26. I'm finishing my master degree in the University of Maribor.
My name is Alberto Favier. I am Italian and I come from Brescia. I'm a flight test engineer here in Pipistrel.
The hackathon starts with an introduction by the project leader. They explained the problem that we were trying to solve, which was basically future green aviation, sort of a microfeeder concept. And then they also assign you a team. So we started with a team of 4 people per team. And then they just say at 6 o'clock in the afternoon, now you can start working on your problem. And in 48 hours we want to have the solution.
The aircraft that we developed for the hackathon was a 10-seat electric aircraft that had the purpose of provide a service between unprepared airfield and airports. The thing that made us win, I think, is that we really thought about the experience of flying that aircraft, not just the aerodynamics, not just single aspects of the aircraft.
So I decided to enter the MAHEPA hackathon because it was a very interesting project, a very interesting event. You have 3 days to design a concept aircraft. Generally, events like hackathon I would recommend to everybody because this event can be used in different industries, in different settings, in different situations, and it is a very social event where you try to come up with a solution relatively fast.
I have joined the flight test team, and which is really incredible for me because I can actually fly the aircraft and see the results in flight of all the design and construction process. I'm learning a lot. The environment is really competitive, so there's no time to pause. But it's nice. It's really interesting, and I would suggest to all the people to find a company like this.
If I didn't go to the hackathon, I would have never met the people from Pipistrel and I wouldn't end up like doing my work here now. And I'm really grateful for the fact that I have this opportunity. It feels like we are really trying to revolutionize the part of the aviation.
My name is Fabrizio Gaspari and I work in Slovenia for Pipistrel Vertical Solutions. What I like about MAHEPA is that it brings theory into practice. For me it's a very nice thing because I just graduated 3 years ago, and so at university I only saw theoretical things, but here we are developing 2 very innovative aircraft and we will make them fly. You cannot say that this project will change the world, but we have to start somewhere. I think that this kind of project could create the flow for a future better environment, so we can use this aircraft to show to the world that this cleaner aviation is possible. Innovation and fun.
My name is Lorenzo Trainelli. I am an associate professor at Polytechnic Milano and I work in the Department of Aerospace Science and Engineering. Aircraft design tasks and in the prediction of scenarios of usage for new fleets of hybrid electric aircraft. This is a very exciting topic because it will have a strong impact on the future of our lives. It will change aviation, starting with small aircraft, but going towards regional aircraft, which is one of the main themes for our studies.
I am Grace Neubauer and I work at the University of Ulm. I work as a research assistant for the cooling design for the hybrid Panthera. There's a lot of aspects that we all like, of course. I think biggest for me is the collaboration between different parts of the European Union. We have different universities and companies working together for the one outcome. We are producing 2 very different aircrafts, both for the same purpose, and I think that the most interesting part is definitely the collaboration.
My name is Jan Schirmer. I'm working at DLR, German Aerospace Center, and I'm working on fuel cell and battery system development. It's a platform where we can develop our systems and demonstrate and test and evaluate our systems and our developments. So it's a very good tool to have possibilities to make new things happen and to test it in the real environment. So, but it's for sure also the first step for next steps for bigger aircrafts, for scale up of these propulsion systems that we can use then also for passenger aircrafts, maybe in the regional range. And also to compare this with other options of hybrids, for example, to compare this with the Panthera system, so to see where we stand with the new technology of hydrogen and fuel cells.
My name is Alfred Falger and I come from Compact Dynamics. I'm the project manager for the propeller drive systems and the Rotax generator engine. It will have an impact, but I think it will take some years that people are ready to fly with electric planes, but we have to work on and on and on the next years, and I think it will be a good concept. High power electric drives for airplanes.
My name is Masha Kamaksel and I come from University of Maribor. In the project we are responsible for doing the transport studies. We are researching how these new aircraft will be used in the new transport services. We are also thinking how to charge them. We are doing the ground infrastructure, all the equipment that is necessary. We are thinking about how the airport is going to change using this kind of aircraft. It will introduce a technology that has a less effect on the environment. As we've seen till now, these aircraft are less noisy, have less emissions, and we can think about it how to use this kind of aircraft nearby the cities, in the airports that now the conventional aircraft are not allowed to fly, so it will change the way we will travel.
My name is Fabrizio Oliviero. I am a lecturer at Delft University of Technology. I am responsible for the work package of scalability of the powertrains and aircraft design. Gives the opportunity to share experience, motivations, and different point of view on a really interesting topic that is hybrid propulsion for aircraft. The main outcome is to show to general audience that flight in an alternative way, more sustainable, is actually possible. Sustainability, and the other word is collaboration.
We all wish to live in a clean and safe environment, but due to the increase in high air traffic volumes, our impact on the environment is still increasing. In order to reduce emissions and provide cleaner technologies for future air transportation, a partnership has been formed in 2017, which launched the European-founded project MAHEPA under the Horizon 2020 program. The MAHEPA project is not only developing new key powertrain technologies, but it is also building a roadmap for future market implementation of hybrid electric aircrafts. In the future, when air travel will increase, clean technologies such as the one developed in MAHEPA will help to obtain a safer and cleaner environment and will enable us to travel around the world fast, green, and cheap.
My name is Thomas Koopman. I'm from the Netherlands and I studied in Delft Technical University. I did aerospace engineering.
My name is Christian. I come from Slovakia.
My name is Vasek Plesec. I'm 26. I'm finishing my master degree in the University of Maribor.
My name is Alberto Favier. I am Italian and I come from Brescia.
Good afternoon. Welcome back to the MAHEPA workshop on safety and HMI consideration in hybrid electric aircraft. We are ready to start with the second part of our workshop, which includes two talks. The first one is on engineering HMI requirements in hybrid electric and electric aircraft, delivered by Paolo Romagnoli from Pipistrel Vertical Solutions. The second one is titled The Pilot's Point of View, Ergonomics and Workload Considerations by Johannes Anton from H2Fly. Both Pipistrel Vertical Solution and H2Fly are companies that take part in the MAHEPA consortium, along with Compact Dynamics, with DLR and 4 universities, University of Maribor, University of Ulm, Polytechnic Milano and Technical University Delft. So we're ready to start again, giving the floor to Paolo Romagnoli for his talk on engineering human-machine interface requirements in hybrid electric and electric aircraft. Paolo, the floor is yours.
Thank you, Lorenzo, for the nice introduction. So a little introduction of myself. I'm Workpack 7 leader in the project MAHEPA flight test, together with Alberto Favier. And currently at Pipistrel, head of design organization, and I have a background in flight testing. I've been 5 years in flight testing, as well as I'm private pilot and flight instructor. So this is why I'm here to present this this section of the workshop about the human-machine interface. Just from the grant agreement of the MAHEPA project, the task 1.4 was the task to develop the human-machine interface. So what is behind this acronym? With human-machine interface, we include all the let's say all the cockpit environment, which includes the system operation, the normal flight, the navigation, the communication, and as well as the emergency devices. So for the the challenge that comes from the development of a new generation of power plant is how to transfer the testing, which happens normally in a lab, with the interaction with the machine, which is done for a lab environment, and transfer it into the cockpit. So with the MAHEPA project, we reach a very high TRL. So the two airplanes were actually flying. So this means that the test platform was airborne, and in this case, all the systems of the hybrid power plant had to be operated by a single pilot in the cockpit. This posed quite high challenges, which we can divide basically in three groups. One is the cockpit display, how the pilot was informed about the status of all the systems related to the power plant. One is how the pilot controls the power delivered from the power plant to the propeller shaft, and one is how to communicate to the pilot any malfunction or any value which reaches a value which is not in the foreseen operating range. All of this needed to be simplified at a level which would be possible to be managed by a pilot in a way that his workload would not be increased too much, I would say, compared to the normal operation of a conventionally powered aircraft. So the pilot workload, and this I don't want to overlap with the following presentation from Johannes. He will speak more in details about the pilot perspective. It's one of the key points. So introducing complexity, as we mentioned several times, introduces also potentially complexity in the operation, in the normal operation. So we did operate in a flight test environment, but we have to conceive the systems for the real products. So finding a way to concentrate the informations and having a pilot operating smoothly and with a reduced workload was the main target of the task 1.4. Okay, the deliverables related to this task are the 1.7, 4.4, and 6.5. I will go quickly over this. If we look at the architecture, so the whole principle of the MAHEPA project is around the modular approach. So from this slide, we can see how the two test aircraft, so one with the internal combustion engine, the Pantera on the left, and the HY4 with the fuel cell hybrid power plant on the right side, they share the same modularity. So the architecture of the two power plant, despite the different nature of the PGM, so the power generation module, which in one case is the internal combustion engine and in the other case is the fuel cell, the general architecture is the same and is shared between the two test airframe. So we have an energy storage module, the batteries, power generation modules, which we already mentioned, and a PMCD, which is the main brain of the whole system, so power management, control, and delivery. And then we have the final thrust delivery module, so namely the electric motors and the propeller. All this provides and all the systems that have their own values, let's say their own parameters that are being monitored and actually manipulated. and needed to translate into an human-machine interface for the pilot, where we had to find out a way to have a modular approach, so to find at least the first layer of the HMI should be common between the two test aircraft, while the second or the third layer of the display could be obviously different because of the different nature of the PGM module. So I would say that as I already mentioned, the excessive workload was the main risk. So also from past projects which we ran in Pipistrel for pure electric aircraft, and also together with the DLR in 2016 for the HY4 project, we found out that to simplify the level of information provided to the pilot and to simplify the way the pilot operates the machine, it's a challenge, and this will be more and more as soon as Fabrizio Oliviero mentioned, as the architecture of the airframe also evolves in direction which could bring to even more complicated architecture, let's say distributed electric propulsion or different hybrid systems. So with this in mind, we came up for the Pantera hybrid with this cockpit layout. So where you can see, I didn't put a comparison with the conventional powered Pantera, but if you see this cockpit layout is 75% common with the normal Pantera. So one would expect a dramatic change in the cockpit layout and a complete different set of avionics. But as you can see here, all the instruments that are numbered, apart from instrument number 2, which I will talk a bit more later, are conventional. So we have a normal Garmin instrument for the normal flight operation and engine monitoring of the Rotax, which is the internal combustion engine selected for the Pantera MAHEPA. We have a normal Garmin G3X in the middle for the navigation, communication. We have the classic Garmin GPS and radio and communication and transponder and ADS-B, which is really the classic one we have on the serial production Pantera. We have as well a backup instrument, number 6, the small one is the Garmin G5, which is an independent instrument with a backup battery, so this provides the minimum number of information for the continuation of flight in case of full avionics blackout. And the classic landing gear controller and flaps controller, which we also have on the normal Pantera. So the main differences here are in the display located on the right side, which we named MPCI, which stands for MAHEPA Power Plant Control Interface, and the switch panel, which is obviously completely different. So I will speak more in details about the MPCI later. The switch panel is quite interesting here. We have master avionics switches, the same as we have on conventional aircraft, but here the function provided by the master switch and the avionics switch, actually the avionics switch has the same function, but the master switch here just turns on the PMCD. Then we have the battery system start, so this connects the high voltage batteries to the PMCD. We have the generator start, which is a soft button and controls an algorithm that performs the whole startup procedure of the Rotax 915 and the electrical generator. And then we have the two main switches. On the left we have the battery mode, on the right side we have the generator mode, and when both of these two switches are switched on, then we are operating in hybrid mode. The last one is the throttle switch, throttle enable switch. This is required because the throttle is a fly-by-wire throttle, if you want to read it in this way. So it's a position sensor of the throttle lever, which detects the power required by the pilot. And this information goes to the PMCD, which transforms it into a request of torque for the electrical system, for the power plant in general. So why you need a switch here is because in case you park the airplane and somebody touches the throttle and leaves it on a halfway, let's say, and you would turn on master avionics and all the power plant switches, it might be that the system powers up and the propeller spins. We do have software protection in place for this, but to have a hard switch is also an additional safety feature. This is how it looks in reality, the cockpit layout of the MAHEPA Pantera. So we have for the avionics we already discussed. In the middle of the two seats we have the black lever, which is the throttle lever we discussed about, and we have the propeller RPM controller, which is still separated from the main throttle control. In a future development, we will maybe talk about this later, it's envisioned that also the RPM controller gets integrated in the automation behind the power plant control. So in this case, the throttle lever basically senses a request of power from the pilot, or let's say torque, and then sends a signal to the PMCD, which computes a value of torque, and then finally the torque is requested and converted into a current request for the electrical motor spinning the prop, and this power request is satisfied by both the batteries and the power generation module, and this the proportion is shared and decided by the PMCD. In addition, just for the flight test campaign, we had a fully instrumented aeroplane, and to monitor all the parameters recorded and measured by the FTI, we installed an FTI display on the right side for the flight test engineer. So if you go a little bit into details, on the display, dedicated display, the architecture, the final architecture for this test aircraft is to divide in 5 layers. The main layer, as said, had the scope to be more as much common as possible with the H54 one, while the other 4 are more specific to the ICE hybrid configuration. So what we see here, again, the number of parameters that run on the CAN bus are hundreds, as you can imagine. We had to select the relevant ones and display them in a fashion where the pilot could get easily access to the relevant information for the safety continuation of flight, and not more than that. But at the same time, we have to be careful not to reduce the number of information at the level where some precious information is not then displayed to the pilot. So on the left side, we have a classic indication of power and RPM. I say classic because we produce electric aircraft since a few years, so we are used to indication of kilowatt, which may be not so conventional for the rest of the audience, but so on the upper side we see this big number is the actual power on the propeller shaft. The lower arc is the power delivered by the internal combustion engine in this moment. Actually the one generated by the electrical generator. Below we have the propeller RPM indication. And then we go to the more interesting part, which is the center right side. On the top, the first line indicates in which mode we are operating. It could be battery, generator, or hybrid. And this diagram here shows the 4 main components and their status. So the color of the rectangle around the module is indicating that the status of the component is okay. It turns amber or red in case you have any caution or warning related to that component. We'll go back to this topic later. These arrows which you see, I believe you can see the cursor, yeah. So these arrows here, they are a graphical way to display in which direction the energy is flowing, if you want, or the power. Depends how you see it. So normally we have all the arrows pointing on the right side. In case of the recuperation mode is activated, we might have some power coming from the drive to the PMCD, and the PMCD then transferring it to the batteries. On the lower part, we have information about the fuel quantity and the battery state of charge, which they are combined because they are both linked to the remaining flight time, if you want to call it this way. Again, this is a flight test aircraft, which is operating in flight test environment. So here the pilot is trained to basically decrypt this information, because on a normal pilot would not get what it means to have another 20% on the batteries and 150 liters of fuel. On the future, it's envisioned and actually suggested that this information here is combined in one single synthetic number, which we have, for example, on the Velis Electro, which is called RFT, remaining flight time, which is an algorithm that takes into account a number of variables and provides the pilot with a very direct information of remaining flight time in minutes and hours. So again, this was enough design for this project, but it opens up again, margin for improvement for sure. On the number 7, we have classic temperatures of the electrical components, so the motors, the 2 inverters, and the 2 batteries. And then on the bottom right, you have the black screen for the CAS messages. CAS messages are crew alerting system messages, and we will see later. So here you will have, in case of any failure warning or caution, you will have a list of the ongoing, let's say, suboptimal or non-nominal values. The second layer, it focuses on the drive side. So the 2 motors and the 2 inverters. I will not go too much into details of which numbers are displayed here. Are mainly, let's say, values which the pilot may look at in case he has some troubleshooting. It is intended to be displayed in flight, but as you can see, it's not as user-friendly as the first layer. On the third layer, we have the PGM screen. So this is obviously dedicated to the power generation module. On the first line, number 2, we have the fuel quantity. In this case, it's splitted right and left fuel tank, because we have 1 fuel tank per wing. All the drive numbers are squeezed on the left side to leave more room for the internal combustion engine specific and the electrical generator specific values. Again, I will not read them all, but as you can see, these are the bare minimum number of parameters which the pilot might be interested in. In general, the general rule is if everything is green, everything is good, and the pilot should not lose time or lose his focus on flying the aeroplane to look into every line of this screen. So I will talk about this a bit later. So the last, let's say, the last layer intended to be used in flight is the battery, and this obviously shows values related to the right hand and left hand battery packs, which are again in the wings. Which includes state of charge, state of health. So the state of health is a quite complex algorithm that takes into account, again, a number of variables related to the battery box and computes a synthetic number from 0 to 100 that basically informs about the status, the aging of the battery pack. Current information, voltage information, it's not really something that the pilot would look for, but is there for eventual troubleshooting. And then other, let's say, information like voltages, temperatures, and the delta between all the cells values, and the maximum difference between the minimum and the maximum measured inside the box. The PMCD layer is the last one. This is not intended to be used in flight, so this is not for pilots. it is mainly used for troubleshooting and for maintenance. So here more detailed information are provided per each component. So you can find the drive, PGM, and inverters again, batteries again. So all what we've seen so far, it was what is displayed to the pilot in case of normal operation. So when things and components operate as intended. What happens in case any value reaches, say, approaches one of the limits, so approaches the end of the intended range, or even exceeds it. So we have two levels of messages. So one is the caution and one is the warning. So the caution is usually displayed when the value is still within the range, but it's approaching the limit. And the warning is displayed when the limit is exceeded or when a component has a complete failure. So what happens in case there is a detection of a failure or a value that is exceeding the intended range? A big message appears in the main screen, and the pilot has to press the acknowledge button to confirm that he read the message. And then we will see later, so the message disappears from the main layer and gets marked in the bottom right side where the CAS messages are. So there is a physical input from the pilot to confirm that he actually read the message. And then we have an if here, so if the failure condition is still present, then the caution message is kept there until the failure condition disappears. Or in case the failure condition disappears, then we are back to normal, so to the point one. The corrective actions are defined, in our case, in a test environment. The corrective actions are defined flight by flight, depending on the mission. And depending on the failure mode or the parameter which exceeds the range. And in case of normal operation, if we envision a hybrid power plant used in a normal operation, so in a certified world, then the corrective actions are defined in the pilot operating handbook. This is a little bit detailed so that you can see a little bit better. So there is a very big message in the middle of the screen which the pilot cannot miss. This is also associated to an aural warning through a speaker and also in the audio panel. So the pilot listens the warning also in the headsets. And after acknowledge, the message goes in the CAS messages box on the right side. As a conclusion, or maybe food for thoughts, the complexity level compared to the pure electric is quite noticeable. But despite this, as we have seen, the additional components in the cockpit layout it's only one additional screen, the same as the pure electric. So this the need to concentrate more information in a single place. This is again it opens up a wide number of options. How to deliver the proper and the minimum, but at the same time all necessary information to the pilot. Certification aspects need to be investigated given the complexity and the novel operation modes. This includes the design aspects as well as the pilot training. So one thing that we also gather in experience with electric airplanes and with the MAHEPA project is that the training of the pilots definitely is something that increases the level of safety up to a point where it's now, say with the new generation power plant, definitely it's opening up a complete new generation of pilots as well, if you think about the new generations, or requires the legacy pilots, let's call it like that, to really rethink how they fly the aeroplane. Not a lot in the normal operation mode, because this should be taken care by the design to simplify it. Let's say single lever operation and a big brain behind that thinks about operating modes and power delivery and draining the power from different sources. But on the abnormal situation, then pilot training becomes crucial. And the last thing is that whatever you've seen in the slides before, it's definitely the HMI developed for the project, but the margin for improvement is quite big. HMI is something that during the story of a project, it keeps developing until the design is freeze. It's very hard to design the HMI on the table. You will always find out by flight testing and by certification activities ways to improve it, and bigger changes or smaller changes to the way you set up the display and the information provided. So this, let's say, just says that what you have seen is okay for a research project, but definitely it could be developed in several directions. So more interactive, or in artificial intelligence, or you name it. So that's it. Thanks for the attention. Yeah.
Thank you very much, Paolo. Fascinating, definitely. Looking at the pilot's perspective on board. Great achievement that actually led to the flights, led to actual flight campaigns, flight test campaigns. So I think we might pass to our next panelist, and I'd like to, as I did in the first part of the workshop, I'd like to invite our online guests to pose questions to our speakers in the chat on the YouTube channel. So we will read your questions to our speakers for the final panel discussion. And I'd like now to give the floor to Johannes Anton from H2Fly. Johannes, you're connected online. Can you hear us?
Yes, I can hear you. Can you hear me too?
Sure. Please, the floor is yours. Thank you.
Okay, thank you very much. I hope you can see my first slide here. I think that is the case. So yeah, thank you very much for the opportunity to present here. I was asked if I could present a few quick thoughts from the pilot's perspective. So I was one of the flight test pilots in the HI4 flight test campaign back in 2016 and 2020, so almost exactly a year ago. And like Josef pointed out before, we were in the team that was flight testing in Maribor was completely in isolated condition, but it was a challenging time, but also very rewarding. And I think back to the time to Maribor with a great joy. So greetings to Maribor. So the 2-3 points I would like to add to what Paolo already gave a very detailed view is kind of the bigger picture perspective from the pilot's perspective. So let's see, there it is. So quick overview. I will quickly talk about the HMI for the flight testing versus product, which Paolo also pointed in the direction already a little bit. Then give you a few examples how we intentionally chose to do it in the HI4, also in the aspect that it was already flying, as I said, in 2016. And then the second part, a few thoughts in the direction of automation versus pilot engagement, kind of in the very long term, so 10 to 20 years. If you look at the HMI you want to have in the product, kind of rough schematic is almost as in the fuel cell car in this case, one push button and it turns on and it does everything itself, so all the power management and so on. In the aircraft, of course, you have a few further systems that are kind of the old school systems like avionics and so on, where you have a few extra buttons and you maybe can switch between 2 or 3 hybrid modes. But this is kind of what we would like to have as a simplified, highly automated interface, like also was shown in the talk from Paulo before. For the flight testing, we intentionally chose, especially for HIVE-4, for the initial flight testing, have several functions kind of taken away from the automation and kind of hardwired. For example, for fuel cell stacks, so that you have a very low part of automation of some dedicated parts of the system, to make sure that you, as the test pilot in that case, choose the parameter set or the state of those systems, and you can switch off one if you choose, and can also test anomal situations. But it also kind of gave the chance to not rely on a high automation from the very get-go, which means reduced testing of software and hardware in the loop, and basically get it flying early and quickly. As you can see here, it was kind of a challenge to get that many small switches and buttons included in a relatively small panel. But after quite some headache, I think the team found quite a good arrangement. It looks simple, but it also took some time to then develop the checklist so that you can have a cockpit flow kind of left to right, up to down, and have a good situational awareness of the state of the different systems that you chose. Yeah, here also to give you a quick overview, as you can see, the initial HIVE-4 version had a bit of a more simplified generation of the earlier HMI system, but still already quite intuitive. Bear in mind, this is designed for the flight testing again. So for a product, this would be even more intuitive and simplified, but especially during flight test, of course, we like to see the absolute numbers and not just the implicit values or range and so on. And then, of course, also in the flight testing arena, you have a lot more subsystem pages where you can, for example, just to show one, look at the single cell voltages of the battery, and then also of the fuel cell stacks, and you see the pumps running and so on. This is merely for, on the one hand, troubleshooting, or on the ground before you take off, double checking all the systems that they are running as expected. But again, this is something that you probably wouldn't see in a product. You would more or less overwhelm the user itself. Then, as I said, in the implementation of those different functions, we very intentionally thought about which of the systems do we want to have on which automation level, or on the hardware. You can think about it as the highest level being software controlled. So, for example, if a cooling pump is running high or low speed, or if a valve is opening or closing, most of those, of course, will be software controlled. But very intentionally, some of the functions you want to kind of downgrade to the second layer, the digital red switch, kind of the digital CAN switch, which still goes via the digital bus, but you would then switch it manually and take care of that. And the very basic level is the hardwired switch. So you have some very important functions, or kind of the live signal, for example, for a single stack, that you want to make sure there's no even the slightest interrupt. For again, at least in the flight testing version, you want to make sure that since you don't have to automate, you intentionally choose some of those systems to have manually operated, and then you can be sure that there's no small sensor spike or misread, and that would then lead to a stack shutdown or something like this. That, of course, later in the testing and certification, you make sure that all of those are cornered out and all the small corner cases are taken care of. Then taking this thought of automation on the system level to the pilot level, if you look at the pilot, now very big picture, so in the next 10-20 years, we will get to the point where the pilot kind of gets only as an optional pilot or safety backup pilot, and the system from start to finish does this whole thing. And then the next step, of course, would be having a remote pilot only from the ground in the case of kind of the automation gets to the point where it says, okay, please take over. It's safer now to do kind of emergency procedures or whatever from a pilot. But once you go fully autonomous, then the good news is it's quite easy, because in the air, the corner cases are less than, for example, on the ground transport, and you don't have to keep the pilot informed. And the challenge in the next 10 to 20 years basically is, as long as the pilot is on board, you have to keep him or her well informed and engaged. And so here on the left side, you basically see the performance level is peak when you have a medium level of, they call it arousal. So basically it's similar like in the theory of flow, where you have a very small bandwidth where you have a task that is not too hard, not too easy, and you're basically at the optimum level of engagement and arousal, and so your performance can be optimum. And once you go highly into stress, you get adrenaline running, and basically that shuts your logical thinking down. You get anxiety, worst case panic. On the other side, and this is what I would like to talk a little bit about, is once you get out of the loop, so the automation level is so high that you don't have to think a lot, and it's doing its thing, going along, everything is nicely, you kind of get to the mild alertness or even boredom, let alone sleep. But it means that to prevent this, you have to make sure that the pilot is still kept in the loop and has a good situational awareness. And just a few thoughts in this direction without going into it very deeply. It's a very big topic, but I just want to give a few hints. So the latest research from the last couple of years that you can find, in this case for level 2, 3, and 4 autonomous vehicles on the ground, also applies in the big picture approach to what you would like to do kind of for the next big step in the next 10 years for highly autonomous systems. So not just the powertrain automized, but also the kind of the whole flight. And there the rules, they almost sound like they were written by Captain Obvious, but bear with me. So you want to provide a high required understanding of the autonomous vehicle, aircraft in this case, the capabilities and the status. So that also means that you have to make sure that the pilot or user in general does not over or underestimate the capabilities of the system. And that at the same time then interacts with point 2, where you can say you want to engender a correct calibration of trust. Again, we've seen this in the recent years already with some of the autonomous driving systems. Some of the drivers overestimate how well the system already understands the surrounding, and when kind of is the limit where the system asks you to take over, and that can in some cases be in a very late moment. Very rarely in the air, it's way less corner cases again, but the big picture is kind of the same. And then third, you want to stimulate the appropriate level of attention and intervention, and this is kind of the big point on very early. So design the avionics system or the whole HMI system, and that includes even the feedback you get from the aircraft from any senses. So not just the display, but the overall everything you touch and hear and interact. That this gives you very good situational awareness and keeps you involved in a way so that your attention level is relatively easy to keep up, and you are ready for an intervention. That's at least very important for the initial phase of automation. And then that also leads to the claim that you need to minimize the automation surprises, and they that's nothing new. Like you know those famous sentences in the Airbus. It's oh, what is it doing again? And or like that one has never been done before from the system. And so basically think of the pilot when you design the system, and try to be very active in the feedback loop that you give the pilot, so that the surprise level is kept to a minimum. And then provide a comfort for the human user and reduce uncertainty and stress. And this also relates especially back to the surprises, which would give stress, but then also to any emergency procedures and abnormal procedures, that there's no sudden stress increase, but that you rather have a kind of predictive code that says, okay, our level of uncertainty raises, and I would like to alert the user or the pilot early on and say, listen, still everything fine, but be aware your attention might be needed, get back into the loop earlier than later. Yeah, and the sixth one is almost too straightforward. It's be usable, but again, those points are just the big picture. If you search for them, you will find kind of the detailed descriptions, what is meant behind it. But the big message is basically try to keep the pilot engaged, take the attention back early, and don't surprise the user too much. Yeah, there you have it. So our experience was for flight testing in some of the automation, it is actually useful for the very beginning of the flight testing to keep the automation intentionally low. And yeah, as we said, for the automation, keep the pilot engaged as long as he or she is on board, and yeah, keep the monkey brain happy. That's kind of the takeaway. Yeah, so thanks for your attention. Oh yeah, and maybe one more word to the team. So it was a great team effort. This is just a small part of the team that you see here, but as you can see, we despite the hard work, we also enjoyed the work. And I want to give a shout out to the whole team. It's great fun to work with you guys.
I'm sure you did enjoy. Thank you very much, Johannes. Very fascinating topic. Again, you brought into the picture underlining the human factors, and this basically drives us to kind of the end of the circle, because in the first part we touched upon very early considerations in design, such as even the identification of a candidate configuration for the aircraft, and we've gone the full circle to the first end user of the aircraft, the pilot, with its human factors considerations that are crucial to safety and to operational efficiency, and then paving the way for the introduction of these new technologies at a broader level. So, any questions for our panelists? We have a question from the conference room. Yasir, please. Wait for the microphone. Sarah is coming.
Thank you. My question is regarding the previous presentation by Paulo. So thank you for the informative presentation. But I was just, it's not a question, but rather a comment or loud thinking regarding the RFT, remaining flight time, right? So an algorithm calculates it based on certain anticipated performance, okay? And let's say if the pilot deviates from the parameters which the algorithm used to calculate the RFT, so the time would be reduced, right? So I was just wondering whether it's possible to indicate that band of performance to the pilot, that if he or she remains within this, so the RFT would be this.
The RFT, as developed till now, it kind of already takes this into account. It's like, it's not completely stupid. Let's say it's not just using numbers which are from a table, but it starts from that and also takes into account the current way the pilot is using the aeroplane. And it's also counting the average certain amount of minutes in the past, how the pilot operated the aircraft, and then foresees how much remaining flight time the pilot can expect. Obviously, it's not a scientific number which gives you, I mean, you will not have the complete loss of power after exactly 11 minutes if it's 11 minutes displayed. But it's a good indication. So within a very, very good tolerance by flight test experiments, the number showed is very close to the experience. So it's a number which cannot be used for flight planning. By ASA law, you have to refer to POH table, which is the stupid way, let's say, the very basic way to compute your flight endurance. But the remaining flight time algorithm gives you a very, very good estimation. It's not 100% accurate, but way more than the table in the POH, which still remains the only valid information for the authority. Yeah?
Thank you.
For the moment.
Thank you. Any other questions? I invite our guests online to pose questions on the chat. I don't see new questions for our speakers. I was wondering, for both of you, if in your experience in the MAHEPA project, this amazing work done in trying to synthesize the information for the pilot, decluttering so many aspects and trying to convey the really crucial information was kind of ongoing work even during the flight test campaign. So did test pilots report something interesting from the flight test campaign indicating possible ways of improvement for the configurations of the HMI that were actually implemented?
Johannes, you want to go first?
All right. Yeah, so actually, yes, that's an interesting question. During the flight testing, we kind of immediately in the debriefing wrote down the operational changes that we wanted to implement to the next before the next flight, and that included small adaptations to the checklist flow, to the startup procedures, but then also to how we would like to gather the information on the different main, but then also sub-pages. Yeah, definitely.
I'd say in general, yes, I can report the same experience when the pilot participated not only to the flight test campaign, but already was involved during the ground test phase a lot. So the pilot showed up at the factory during the assembly of the airplane. Also, sorry, he contributed a lot to the design of the display. If we are just focusing now, I believe, on the HMI in terms of the display, but also the complete cockpit layout. So involving test pilots in the preliminary design phase of the interface, both in the lab or during the ground test phase, where the pilot gets familiar with the system, like simulating the full mission on the ground, which can be simulated. Definitely the inputs arrive, and you still have time to improve the design, which is definitely becomes optimal at the end of the flight test campaign. But you can start with a good base if the starting point is not engineering perspective only, but the pilot is in the loop, in the design loop from the beginning.
I see. Thank you. Any more questions? So I see a question on the chat. I'd like to convey this question from Vincent. How do you foresee future transition training for pilots? The HMI could make these easier, but also introduce new safety risks, as outlined in the presentations. Would you like to start, Paolo?
Yeah. So, yeah, with the risk of, let's say, repeating what already said in the presentation, all aspects of flying are affected by the introduction of a new type of a novel technology, like a complete new powertrain. This is more maybe an experience we had for the current products which we have in production, not that much with the MAHEPA project, because in the MAHEPA, obviously the pilots were qualified test pilots, while the training, which I believe the question is trying to address, is the training of pilots, let's say private pilots or commercial pilots in a real environment. So the experience we had with the pure electric aircraft, which is delivered on the field, is that the design office should be part of the definition of the training syllabuses, which should not be left to the training organizations in this phase, because the design office, let's say, knows the system inside out. Possibly we did experience most of the adverse situation in the flight test environment, in a controlled environment, and we can, any design organization designing an electric or hybrid aircraft has the possibility to steer the training syllabus as well as the regulatory authorities in the direction of providing, again, a training which is sized to the needed and does not need to have a complete understanding of the systems necessarily. If you think about your driving license now, an 18 years old which gets the driving license today, he doesn't have any idea how the internal combustion engine works in his car. So once upon a time we used to explain every 4 strokes, and you have questions also about that. I think we are moving in that direction, and this a little bit links to the automation topic that also Johannes mentioned. It's still everything to be explored deeply, but providing the necessary training, it's crucial, but has to be proportionate to the and to keep the pilot workload low enough, even in normal operating environment, and not to, let's say, create a generation of pilots which are, how do you say, not completely aware of the systems, but at the same time the good compromise where they need to know how to troubleshoot and how to handle emergency situations. I don't know, Johannes.
Any comments on your side, Johannes?
Nothing to add.
Thank you. So I don't see any more questions. Any hints from our guest present in the room? Yeah, there's a question. Alberto? Oh, it's okay.
Do you think that it's time for EASA to start forcing training organizations to teach electronics, currents, voltages, or is still too early?
That's a good question. I would say...
Provocative question.
The answer is it depends. It depends on the system complexity we are talking about. So the pure electric, I believe, is completely manageable by a pilot who knows how to operate an internal combustion engine. We have this experience from the field with the Velis Electro. When number of propellers spinning becomes 12, or you have hybrid number of fuel cells here and there, probably the pilots should also learn about the systems. That's my opinion, maybe.
Johannes?
Yeah, I would say so. It will be natural that you will learn about the different physics behind it. With the battery electric, it's relatively straightforward. But even with the hybrid systems, in the end, the operation will be very simple. And yeah, maybe that hasn't been mentioned today too much, but it's a great fun to fly those hybrid electric aircraft. They are a completely different experience, and whoever has flown one and you talk to them afterwards, you can see the joy in their faces. So yeah, so I guess we will see this technology being taken by the customers quite happily.
Thank you. Okay, maybe I may pose a final question to close the panel discussion. It's something maybe, I don't know, maybe some leap in the future. But do you think that this effort in trying to simplify and convey the important information from such a complex background with so many different components and everything in the architecture of hybrid electric aircraft could be a motivation for a transition to a new way to see the HMI from the very start, like immersive environment, visionics, so changing the paradigm from the typical general aviation or relatively small aircraft or civil aircraft to a way to fly which is more intuitive, not based on numbers, but maybe more on images and colors and indications on, for example, the margins with respect to the flight envelope and things like that. Is it possible that hybrid electric would motivate even more towards this new way to approach the control action and the supervision of the flight?
So let's say my opinion is that there is not necessarily a link between the power plant innovation and the cockpit innovation. The system we are thinking about is very close to what we have already right now in the existing, if you think about the FADEC systems on general aviation aircraft, it is more or less what we are talking about. So a single lever operation and few information displayed to the pilot, and then the rest is taken care by the FADEC. It's more or less the same approach. If the hybridization of the power plants will enable a complete new pilot interface also for other functions. So if I understand your question, you think also about the flight part, so the attitude, airspeed, or whatever traffic information, navigation information. I don't necessarily see the link between the innovation in the way you provide power to the propeller and the rest of the cockpit environment. But that's my opinion. I don't know.
Thank you.
Yeah, I guess it's probably indeed not directly coupled to the powertrain, but I mean, since those powertrains we're talking today about are more digitalized, it's easier to kind of have those technologies converge. And I guess especially augmented reality will be a very interesting thing to watch, how this can completely change the interaction in the cockpit and kind of the natural interaction of how you present the information, the relevant information to the flight crew.
Thank you. Thank you very much. Okay, I don't see any more questions, so it's time to close the panel discussion for this second part of the workshop dedicated to HMI and novel cockpit environment related to hybrid electric aircraft. So I'd like now to conclude this event by calling Dr. Tine Tomasic, CTO of Pipistrel Vertical Solution, to animate a final discussion for this workshop. Thank you, Tine.
Thank you, Lorenzo. Thank you all. The session is titled The Discussion, so I'll still welcome any questions that might come through the medium. But I think it's worthwhile to reflect back, not only on today, but on the whole 4 years that MAHEPA pulled such an amazing group of people together and achieve really groundbreaking things. So if you take a look historically, every single great story in humankind goes along exactly the same lines. The world is the way it is, something happens, the world gets better. In order for aviation to become a better place for the planet, many things need to happen. Many things are happening, but still we are a long ways out. The goal, however, is very clear, and I hope that through the sequence of today and the public events, the team was able to shed some light into how complex and elaborate the challenge actually is. I think if I'm to dissect the messages of today into logical groups, I would try to position them into 5 pillars. The first one, perhaps the strongest one, is safety. I think we noticed this connotation in every single topic that was presented, from fundamental powertrain architectures all the way to what the pilots see and anywhere in between, including from the regulators. I think this is paramount when anyone is doing innovation in such a critical sector of the industry. There is a lot of innovation opportunity. There are a lot of concepts being floating around, a lot of experienced company and a lot of newcomers. I would really plead to everyone that is trying hard for a better place in aviation to take on the responsibility on their shoulders and realize that it only takes one mistake to put a wrong image on the future of aviation when these new technologies are being embraced. The second pillar is what I could call the importance of ecosystem, or maybe a transversal approach to these matters. MAHEPA, at its core, is a powertrain-centric effort. Yet most of the topics of today revolved around other matters. So yes, the mantra of aviation design, that engineers kind of built the aeroplane around the engine, still stands. However, here also the operations and other matters which needs to change also revolve around the opportunities and advantages these new powertrain architectures unlock. So the message to everyone trying to do similar things is that there is no such way, no such possibility to focus on one single area alone and disregard everything else. One cannot live in a bubble when you develop new solutions for hybrid electric aviation at large. Everything is intertwined, and this speaks to the value and power of consortia which come from very different backgrounds and bring very different industrial or academic expertise to the table. The third pillar, and I think this was also quite monumental in today's discussions, is open innovation. How many times do the industry and academia discuss publicly about what they innovated, especially in aviation? Most often, the best, coolest, most interesting things are left behind closed doors, yet here this is an antidote of this statement. And it would be great if the rest of the industry followed the example and opened up, at least partially, so that people who are putting in their lifelong efforts into these topics would not have to repeat the mistakes somebody else has already done. I think it's an important message that in this moment in time, when we are not talking about incremental innovation, we're talking about a paradigm shift in aviation, it's important to stay open so that progress is faster and in the end, safer. Fourth pillar, team effort. I would like to echo what Johannes said just during his last statement. This truly was a team effort. MAHEPA and their partners, of course, carried the majority of the work, but there were many other stakeholders which were indispensables. Aviation authorities, airport authorities, fire brigades, rescue teams. You would not believe how many people were involved in the flight test effort, who were witnessing these new technologies for the first time. I will never forget the vision during the flight test campaign where a firefighter fully equipped, like an astronaut, asked, where do I cut if something goes bad? It's this kind of dedication that we saw in the project, embracing the seriousness and the magnitude of the challenge. And pillar number 5, room for improvement. I think you have heard it from every single presenter, admitting that there's plenty room for improvement left. And I think this is a healthy attitude to the size of the challenge, and also admitting that there is a long runway ahead of us if we want to do it properly. To Fabrizio Gaspari's point, you have to decide at a certain point what is good enough for this particular stage. And I'm happy that we were able to openly and publicly discuss as to where we, as the MAHEPA team, believe future improvements should first be tackled, and what are all the opportunities around for us and others to tackle in order for hybrid aviation to become a reality. So where do we go from here, and how do we do it? I don't have a crystal ball, nor do I have the, let's say, recipe in how to do it, but there is one universal recipe for anything one wants to do if you want to do it with 100% certainty. You need an incredible team, you need sufficient time, and you need infinite cash. Nobody has all of these 3 components at hand, so you have to go step by step and realize what the challenges, besides the technical challenges, really are. I think that maturation by demonstrating things is absolutely essential. Until you try, you don't really know where you made wrong assumptions. Let's face it, history is full of great ideas which didn't work. There's too many of them out there. So demonstrate, design, build, fly, improve, and then certify. There is no direct path to certification or usage. So there's always these infinite intermediate steps almost to get things done. Something that was not touched today, but is an intrinsic matter when you discuss wider use of this new technology, is of course its cost. If the cost of these new products, if the cost of operation is not attractive, it's not going to work. So one has to truly face these tough questions and shape the products, the solutions, so that they also become commercially viable. After all, this is to power a whole new air transportation industry. The industry that we know it today is full of anxiety and has the fear of the unknown for these technologies. This is also why demonstrations are so powerful, why exposures to the relevant end stakeholders are so valuable. And here we come to the education part. We have excellent educators from the European landscape present in the system, but they are typically involved in a one-way street when it comes to education, right? They set new engineers, new talents on course for their lifelong work. What very few people are doing today is educate the stakeholders, not the students, but people who are today decision-making in relevant industries. The airlines, the airport authorities, the aviation authorities, standardization and policymakers. So we all have to stand together and take time to educate, to teach not only test pilots, but also the end users. After all, you see it many times mentioned, my aeroplane is better because it's a hybrid. It's cheaper to operate because it's a hybrid. It's more environmentally friendly because it's a hybrid. Well, really? Many times these statements can be just thrown out there in a blunt way. So education truly is key. And all of this together brings us to something that is truly non-negotiable. And this is winning over public acceptance. Because let's face it, if in the end nobody wants to fly these aircraft as passengers, as pilots, then we all failed collectively. So I would like everybody and anybody to be invited to try, fly, hybrid, electric, battery-powered, anything when it comes to new propulsion technologies in aviation. Try it, experience it, then comment it, then judge it. We are always open for all and any feedback. Please approach us in a direct or an indirect way. And you have our commitment from the MAHEPA team that will definitely be pushing on in the direction that the project has set in the past 4 years. I thank you for all of your attentions, you here in the room, everybody present in the online setting, and I hope to see you next time with even more exciting news. Thank you very much.
Thank you very much. Thank you, Tine. So this draws our workshop to an end. These words from Tine are at the same time celebrating more than 4 years of a strong and very focused effort by a large consortium with a lot of stakeholders and participating bodies helping along the path. It is definitely a milestone in research, applied research and innovation in aviation that definitely will see lots of developments in the future, I'm sure about that. But it's not only celebrating, it's really inspiring. So thank you very much for these final words. I think this is going to inspire the new generation of engineers and pilots and, as you said, also decision makers, people that will have a word on how the next era of aviation will be shaped. So thank you very much, all of you, for participating. Thank you, guests, both here in the conference room in Maribor and online, for your interesting questions. Thank you very much, panelists, the speakers present and online. And let's hope for a great future for electric and hybrid electric aviation along the lines that MAHEPA tried to foster. And all the best, stay safe, all of you. Thank you very much.
Thank you.
With the constant growth of air traffic, the pressure on the environment is rising, and so the use of alternative fuels and powertrains is becoming a necessity. To ease the negative impact of aviation on the environment and to provide cleaner technologies, Project MAHEPA was launched with the support of the EU Horizon 2020 programme. A team of various experts gathered with one sole purpose: to tackle the challenge of more sustainable aviation. Within the MAHEPA project, 2 new hybrid electric aircraft were developed. The first one uses a fuel-driven generator coupled with lithium-ion batteries to power the electric motor, while the second relies on hydrogen-fed fuel cells to produce power-enabling zero-emission flight. The MAHEPA Panthera is a 4-seat hybrid electric aircraft, a quieter and cleaner version of the groundbreaking Pipistrel Panthera that has captured the minds of the aviation community worldwide since 2013. The aircraft provides quieter takeoff and flies with less emissions than a conventional aircraft due to its much more efficient powertrain. Panthera can reach a maximum speed of approximately 170 knots and can fly over a range of approximately 1,000 kilometers. It took years of work and experience to realize the idea of this aircraft.
The MAHEPA Panthera hybrid electric aircraft is giving us a clear example of how it is possible to fly greener. This aircraft has much lower fuel consumption, emissions, and last but not least, it is much quieter. Thanks to MAHEPA project, we are showing that changing aviation is possible, and we are doing it now.
The second aircraft is HY4, a visionary emission-free hydrogen-driven aircraft. The HY4 is the first 4-seat electric aircraft with the most powerful hydrogen-based fuel cell system ever used to fly. It enables completely emission-free flights over short or long distances. The HY4 can reach a maximum speed of approximately 200 kilometers per hour and, depending on the flight profile, can fly over a range of up to 750 kilometers.
Our MAHEPA project gives us the opportunity to develop emission-free electric flight with hydrogen, and together with our partners we can show that emission-free aviation is possible.
The MAHEPA project succeeded in flying 2 innovative aircraft and set a clear roadmap for the sustainable future of aviation.